Okay, what we're going to be covering today is a little bit more into depth with the technical side of things. And this presentation should give you some of the answers that you're going to have that your customers ask you uh, after the product has been purchased and it's in the process of being in production. And this is usually the installation considerations and, wrapping up some of the things that the customer is going to have to do to install the products. And I'm going to review ride-through specifying again a little bit briefly and talk about why we use ride-through, which kind of corresponds to customer specifications. And also, we're going to talk a little bit about connectivity and configuration, and hopefully you guys, being the feet on the street, are going to be the ones that have to field a lot of the questions that the customers have. So hopefully you'll get that out of this. If not, just send me an email or fire me some questions as we're going along. If you can't hear me right now, if you can't, if you're not getting any kind of audio, just go ahead and text me and we'll see what's going on. Okay, just briefly, we're talking about undervoltage products, UPD, uninterruptible power for drives. The industry term is ride-through, which covers all of the different ride-through solutions that are out there, but for our purposes, we're going to be talking about DC bus ride-through. As you probably all know by now, we categorize our products. This is what this slide represents. And this also covers energy storage and charger connectivity and some basic installation and configuration information. Just a quick review. As you know, everything we do as far as standard products, especially UPD products, interacts with the DC bus of a drive. This represents Bonitron standard product connectivity. We're talking about the ride-through, which is the S3534 or S3460 series. The 3534 is covering 50 kilowatts and below. The 3460 series covering 50 kilowatts and above, up to 250 kilowatts in a single unit. We can master slave the 3460s. We've done up to 1,000 kilowatts. Now, just backing up a little bit, as we know that ride-through is usually specified due to utility power events. Every region is going to be different, and by the time we get to the point to where the customer has decided what ride-through, along with help from you guys out there and the Bonitron technicians back here, it's gonna vary from region to region, of course. Usually in the United States we deal with SAGs, but there are some specific outage requirements. Usually we categorize the UPD products into short-term outage, long-term outage, and SAG ride-through. So you're going to be dealing with the utility power events that that particular customer is dealing with, or internal plant events too, with the UPD products being a process level solution as opposed to something like a plant-wide UPS or distribution point UPS. Usually the process level ride-through is another level of redundancy for the distribution point UPS or distribution point backup. Even though you back up for the utility power events, you still could have internal plant issues. But basically we're dealing with environmental issues that take out your AC line, utility power that's feeding the drives. This is another utility power event, uh, and you have a variety of them, from cars hitting telephone poles to transformers blowing up to Smokey the Bear here. And that's what we're dealing with. We're dealing with the time it takes from the utility power event to the time that the utility company gets it back up and running. And that's usually where your specification comes from. It can be anywhere from utility power off up to gen set up. And we'll talk a little bit about redundancy as we go along. Depending on the nature of the application, some applications require several levels of redundancy. Excuse me. And you also have internal plant issues to deal with that can create ride-through events. System and drive fault settings. Some drives have ride-through in them. Some have parameters that have to be disabled, like phase loss and things like that, but that's a very uncommon thing. Usually when you hook the ride-through up, it's pretty much plug and play and ready to go. And so what we run into a lot of times, internal plant switching, load switching, the internal plant power quality situation. So along with the utility power, you have to also be concerned of what kind of events are going on in the plants. And chances are you're going to be dealing with the maintenance guys, the internal plant electricians and engineers, and it's going to be part of your job to be able to explain to them issues with configuration, installation, meeting their specification, any kind of other requirements for ride-through that they're going to have to deal with. So when discussing specification, Bonitron divides the ride-through or UPD products up into three different categories. Three-phase AC line power sags, and that's going to be the majority of your events. So usually in the United States, at least in the United States, we deal with a lot of sag events, 50–60% sags. As long as there's two other phases remaining and they have at least 70% and 70%, we can use a sag ride-through, a single unit you can put next to the drive. Sags are usually brownouts, or when the lights flicker, momentary condition. The ride-through reacts to the drop in the DC bus and immediately holds up the bus so there's no change in speed or torque of the motor. Then the next category that we look at, and this is where you have to add energy storage, because this is a total loss of the AC input for short term. And this is usually caused by utility switching, load deviation. These are some of those internal plant issues I was talking about. Much more infrequent than sags or transients. A very small percentage of utility power events are full AC line losses. Usually in a lot of cases with a full AC line loss, it can turn into a long-term outage, and that's where you bring the generator up, and we usually bridge the gap between AC line loss and gen set up. We usually rate our equipment to the full motor load requirement during an event, because we're providing everything to the drive for that period of time. When the AC line comes back, the DC bus comes back, and then the ride-through shuts down and waits in a static state. Now, as far as these terms out there in industry, Bonitron has developed these categories due to the energy storage capabilities. So we've matched up the energy storage, we've defined the percentage of events, and that's where we come up with all three of these categories. Then we talk about long-term outages, 100% AC line loss, greater than 5 seconds. We used to say that short-term AC line losses would only go up to 2 seconds, but now we're using the heavy-duty boosters to use ultracaps for a longer outage time. So we can do ultracaps up to 5 seconds now. So now going back to the long-term outages, that's when over 5 seconds, up to 30 seconds, a minute, I've even had a request for 4 hours. That just means a great amount of energy storage. We can also provide servo drive protection too. There's no difference to Bonitron as far as a servo drive DC bus and a VFD DC bus. So usually with long-term outages, greater than 5 seconds, we start talking about batteries, using batteries. So the two main energy storage devices we use are capacitors, either electrolytic or ultracapacitors, and batteries. Now, when we talk about redundancy and internal plant configuration, this is usually what you're going to see for a critical application. You're going to have a UPS or sag corrector at the power distribution. You're going to have a gen set that you can switch over for long-term outages. And then you'll have the Bonitron UPD right next to the drive, parallel to the drive, DC bus and the AC line connected. So this would be what we would call N+3 redundancy. There's 3 levels of redundancy here for backup protection. There's the UPS, there's a generator, and there's a process level. A lot of critical applications require this, and some of them actually go up to N+4 redundancy also, especially with data centers. So we actually complement a full ride-through solution for a plant or a process, starting at the power distribution and with the UPS, which would probably be provided by a UPS company or someone other than Bonitron. And then there's a generator backup, and we are the yellow block, which is the UPD. I've been through this in the previous presentation, so I'm going to go through it real quick. There's other ride-through solutions, UPS, AC line sag correctors. Drives have some ride-through features, but it's usually cycles, and it doesn't cover enough to be able to cover some of the utility power events you deal with. There's also active front ends, which also give you a little bit of ride-through, but not, in a lot of cases, it's not adequate to cover the specification. And then there's a Bonitron DC bus ride-through, which is what we provide. With most of the other ride-through solutions, it's going to be a series connection. And as you can see, there's double conversions there, so there's efficiency losses. And there's also an extra point of failure, too. Everything that goes to the front end of the drive is going to be fed into the front end of the double conversion UPS and sent out directly to the drive. So if for some reason the UPS fails, it can take out the whole process. Now there is bypass circuitry in most double conversion UPSs and series ride-through, but still that's a series path, and when you're in bypass, you don't have the backup protection. This is Bonitron's topology. We're parallel to the drive. We don't affect the process during normal operation. We connect to the DC bus. One single conversion, AC to DC. Regardless of which ride-through you're using, it's always just one single conversion. Either you're taking the AC line in the sag and using the remaining AC line and boosting it directly into the DC bus, or you're pulling out of an energy storage device like capacitors and batteries. If you are making nuts and bolts or something that doesn't have a high downtime cost or product damage cost, that's probably not a good solution for, or not a good application for ride-through. We look for critical applications that can have no change in speed or torque of the motor. The reason for that is even though the drive has some ride-through capabilities, and we'll ride through very short events, usually cycles only. But what happens is you have maybe a flow sensor or chill water flow going to a machine tool down the line, and in critical applications there's a much more precise monitoring of exhaust air and chill water and things that are feeding the process. So even though the drive may ride through, the process may still shut down because of change in speed or torque of the motor. In some applications, such as extrusions, there has to be a steady motor speed where you have a good, consistent extrusion. The drive may be continue running, the motor may continue running, but due to a utility power event, it may slow the motor down, and that can cause you to run scrap product without even knowing about it if you're not paying attention. So a whole afternoon of production can be wasted. Once again, the parallel connection, and one of the advantages is we will look at the utility power spec for that particular region, and we can size the energy storage to exactly the specification, whereas say with an online double conversion UPS, usually they start at 5 minutes, and you may only need seconds or you may only need cycles of ride through. So when comparing solutions, you have to keep that in mind. It's very important that we determine the specification before we actually provide a solution. These will work with any variable frequency drive as long as there's DC bus connections, and we also have the digital display for monitoring events and unit health. As you recall in the last presentation, if you sat in, I covered indications and the display and how to do some basic troubleshooting to be able to know what to tell the technician when he actually gets into repairing the unit. That really helps us out if we can get some basic information right off the bat. What are the indicators doing? What are the lights doing? And the digital display is also a diagnostic digital display. That's why I always recommend some sort of a display. We have an analog version, but the digital display really tells you what's going on with the DC bus, the AC line, and it's almost a power quality meter. It does not measure power factor. That's the only difference, but it will tell you what happened during a ride-through event. So that can tell you also, it can confirm what your specification is too, that you've sized the ride-through for. And where this becomes important is that when you specify the ride-through, you may have only specified it for SAGs, but you may find out you're having very short-term outages. We can retrofit SAG ride-through with ultracapacitor, electrolytic capacitor energy storage. Now, we also have come up with a new method of providing ride-through, which is called UPD Lite, and what it is partial power ride-through. Some customers only want to be able to ride through long enough to be able to bring the process back to zero position. So, in other words, you don't need full ride-through power. You can provide enough ride-through power to the DC bus to be able to just hold up the drive until it jogs back to zero position. A good example is robotic arms, things like that. If you lose a reference or lose a drive completely, the robotic arm can damage equipment or cause personnel injury. So that's why sometimes the customer doesn't want full power ride through. They don't care if the system shuts down. They just want to be able to shut it down in an orderly manner. So it's usually you size it for half the speed with the same torque. It's a calculation involved. If we're going to do UPD Lite, it's always an engineered solution, but it's a possibility if the customer is asking for it. Now we're getting into configuration, and This is the issues that you work out prior to quoting, and then later on there may be some further questions about things as they're getting ready to install the ride through. But this pretty much lays out what we need as far as specifying and some of the things that might come up when discussing with your customer the types of ride through or the specification they want to cover. Of course, we need to know the AC line voltage because the DC is directly proportional to the AC line voltage. So it's going to vary. US is always 480. For instance, Canada is 575. So the DC bus is going to have different levels or different threshold levels where the ride through turns on in relation to what the AC line is. We also would like to know, this is not as critical as some of the other parameters we need, but the drive, make, and manufacture, that's just sort of a sanity check. All the guys that specify ride through here have an idea of what the drives can do, and if there's any parameters that may bump heads with the ride through function. Like I said, that's very rare. We've only come up with a couple instances where there were drive parameters that caused an issue. But for the most part, standard drive, the ride through will work just fine. You don't have to do anything to the drive. You don't have to configure it in any way, and it should work properly. And as we know by now, Bonitron is the DC bus guys, so we need to know if there's DC bus connections available. Some drives don't have the bus connections, but they do have kits that you can get that will give you pickoffs from the DC bus. We connect right across the bus capacitors on the DC bus, and you'll see that as we go along. Then also, if you don't back up the control power, there's no sense in backing up the drive. You can back up the drive all day long, but if the control power is wiped out, it's going to wipe out the whole process too. So we want to find out, usually the customer deals with the drive and the control power separately. Control power can be PLC networks, relays, light curtains, things like that. So we need to know what if the control power is handled or how it's being handled, and usually we can provide an option for that. Also, we can back up control power, but in a lot of cases the customer's already thought of that, and they'll usually use a small UPS or sag corrector AC line. It's usually single phase 120. And then depending on integration capabilities of the customer or energy storage sources that they can use, we can provide the integratable modules. And if you look over on the right, each of the different colored blocks represents a module within each of the UPD systems. As I said, single unit for sags, and we add energy storage, a charger, and a discharger for the ultracaps. Because ultracaps can take up to 8 hours to bleed off, and you may have to get into the cabinet in a hurry, so the discharger is a critical piece of equipment for ultracapacitor systems. Batteries, all we need is a voltage regulator, charger, and the battery. Now there's other considerations that you can provide a more economical solution, and that's common busing the inverters of the drives, tying the drives together at the DC bus. The considerations here are the proximity of the drives to each other. Also, the AC line feeds. Of course, on a DC bus, all the AC line feeds are going to be common, but that's something important, especially for the sag ride through. What we would do is we would total up the requirement for all of the drives on a ride-through common bus and size the ride-through to cover all of the kilowatt requirements for all the drives and motors. This is how we specify the ride-through, kilowatts to time. It's that simple. What's the amount of kilowatts for the motor? ride-through can be sized to the motor, especially, even more so than a braking solution or overvoltage solution, because all we're doing is holding up the motor during a utility power event. So you don't have to put in that 150% that you do with a braking solution sometimes, depending on the peak braking power. And all we're doing is sizing it to what the motor requires to run the process. It has nothing to do with regenerative energy. We're just keeping the bus at a stable level. So on the left is the sag protection. Kilowatts to time, up to 2 seconds. The sag ride-throughs will do up to 2 seconds. And then the outage protection, or the outage ride-throughs, once again, kilowatts per time. And if you notice down, if you look at the outage protection block there, on the very bottom left, we can provide electrolytic capacitor energy storage, which is more economical than ultracaps. For the 12 kilowatts and below, up to 1 second, we can do electrolytic caps. Anything greater than that, we would go to ultracaps. If the model number has an S in front of it, it's a full cabinet system that includes all the components for a ride-through solution. If it's an M, that represents each of the colored blocks I showed you in the previous slide. So the block model number, or the unit model number, will have an M in front of it, and a full cabinet system will have an S in front of it. Okay, a few more details about configuring or what you need for sag ride-through. As I said previously, we can go down to 60% 2 seconds or 100% single phase. One thing to also consider is when you have a utility power event and the power comes back, there could possibly be a surge. So you may want to consider surge protection too, some sort of surge protection. The ride-through will not deal with any kind of surge protection. There are MOVs in there, but MOVs can only take a few hits. So if there's a lot of, especially with lightning strikes and things like that, there may be a surge coming back too. So that may be something to consider. You might want to talk to the customer about if that's an issue. For sags less than 60%, no energy storage is required, but in some cases, you may have a sag that's a little bit greater than 60%. Between 60, 80, 90%, you have to add some sort of additional drive capacitance to be able to handle that. But that's when you get down to the nitty-gritty of a specification. And usually, when we get requested for a ride-through spec, customer doesn't know the exact details, so you have to dig in, possibly talk to the utility company to get more information. I think we've pretty much covered this already, but over on the right you see the two versions of the modules, the 3534. They both do 60% 2 second sags, 10 to 50 kilowatts in a single unit, 50 up to 250, and we can master slave the 3460s. Now, ride-through function. This represents the internal circuitry or the boost circuitry for the ride-through. It's parallel to the bus, as we said, but also internal to the ride-through. If you get up above 50 kilowatts in the 3460s, it will have a secondary stage, or it will go in stages of 50 kilowatts. So what that means is if you were to lose a stage, you'd still have 50 kilowatts of ride-through left, and it would be the same amount of time. That would be in a 100 kilowatt unit, and respectively on up. You know, you can lose one phase and the ride-through will still function. So the way the ride-through functions is it watches the DC bus, it monitors the DC bus threshold, and when it gets to the potentiometer settable DC bus threshold, which we do in the factory, we don't recommend adjusting the DC bus threshold in the field. we test them and we set them up for the exact voltage that the customer requires here. So there shouldn't be any kind of adjustments. There shouldn't be any kind of jumper settings or anything like that that you have to mess with once you get the ride through on site and they're getting ready to install it. So the way it works is it watches the DC bus threshold, which is in relation to the AC line. It gets to the threshold level, and then the control circuitry tells the IGBT to turn on, which starts pulsing the inductor. The inductor builds up current till it gets to a breakover point in the diode network right in front of it. Once it gets to that point, it feeds the drive bus capacitors. So pretty much we're just boosting, adding bus capacitance and voltage to the DC bus. It will keep boosting, and the IGBT will stay on until the AC line comes back and the threshold rises to the nominal level, and then you're back at normal function again. Okay, this shows the M3534R connected to variable frequency drive. As you can see, there's AC line connections, and those are in front of the drive. They can connect to the drive terminals, or they can connect up in front of the drive. There is a ride-through disconnect that's included with the cabinet systems. This is a very important component because this disconnects the whole ride-through system. This disconnects the whole ride-through system from the drive. So when you're doing maintenance and you want to lock out, tag out something, that would be the disconnect that you would lock out. As you can see, it's got AC line contacts and DC bus contacts. It's fused at the AC line and the DC bus to protect the ride-through and protect the drive from the ride-through if there's a problem with the ride-through. Usually, when we have issues with installations, we find that it's either connectivity, or it wasn't specified correctly, or maybe it was the wrong kind of ride-through too for that particular application. Maybe the utility power vents are longer than what the customer anticipated, so the ride-through will time out at 2 seconds. These are designed for that, so there's not any component damage or they don't overheat. So it's a 1% duty cycle also. Now, although for SAGs, some installation considerations, but for SAGs, you have a single unit. It can go in the drive cabinet. As I said, I always recommend a DD4 display because it's a fantastic tool for being able to troubleshoot the ride-through, know what the initial indications are. Sometimes it's a simple problem that can be fixed in the field. Sometimes it's not. So the DD4 display will tell you pretty much what parameters are messed up, and it will allow you to monitor fault codes too, up to 30. We usually don't use that screen, of course, because Bonitrons don't fail, right? So in other words, the standalone modules can be mounted mounted inside the drive cabinet, or the customer can provide their own cabinet as long as they have a disconnect and you know, the other busware that's required. Or we can provide the full cabinet systems that have the disconnect, that have all the DD4 display, everything mounted inside the cabinet. You just connect it to the drive. Now, a little bit more about full outage ride-through. Usually you're talking about a 1 to 2 second full outage. Samsung has a 1 second requirement, which is above and beyond most of the other industry requirements for ride-through. And as I said, if you have specified a SAG ride-through, the customer finds out if there's full outages, we can retrofit the SAG ride-through with up to 2 seconds of full AC line loss protection. This matches a lot of the other industry specs that are out there right now. Actually, the UltraCap ride-through was in result of the Samsung specification. 3 types of energy storage, some information about them. We provide energy storage in modules, so therefore when we do a module quote, we can provide loose ultracapacitors as long as you have the integration capabilities to wire them. We'll provide wiring diagrams. It's pretty simple connectivity. You do need to know a little bit about what you're doing, so it's good to have an integrator involved. We package the capacitors in the modules, 700 volt assemblies, and we'll run those in strings to be able to cover the required capacitance for the DC bus. Ultracapacitors, 180 volt modules, 48 volt modules. The capacitors are inside these modules. Just connecting them together and making sure they're properly mounted and connected to the DC bus of the drive. As far as the batteries, we can use any kind of battery. The standard is valve regulated lead acid, and there's no special considerations for the batteries as long as they have the cranking amps to take care of what your requirement is for the ride-through. Our standard units are 4 minutes and 15-minute full outages, and we can derate up to any time you want, but then it gets much less economical the longer the time. So when you have to derate something by half, meaning if you have a 15-minute ride-through, you would derate a 4-minute ride-through for half of that kilowatt requirement, or for 2 times the kilowatt requirement, excuse me. So now short-term outages, all 3 phases, 100% AC line loss. We used to say less than 3 seconds. Now we say less than 5 seconds, because now we've configured the heavy-duty M3460Bs, the heavy-duty boosters, which are rated at 4 minutes, to be able to do the UltraCaps, which are greater than 2 seconds. You're limited with the SAG ride-throughs if you add UltraCaps to them, because they will time out at 2 seconds. And as I said, we've done a lot with electrolytic caps too. We can also, depending on the drive, we have to know a little bit more about the drive to be able to use electrolytic caps by just putting electrolytic caps on the bus without the UPD ride-through. We can do that depending on the specification. We've done it a couple times this past year to where we just added bus capacitance. So if the customer's really budget conscious, they only need a little bit of ride-through, we can look at specifying just a cap bank and not having to add the chargers and the booster and all that. So it depends on how bulletproof the customer wants to be, and it depends on the amount of utility power events they want to cover. It's usually a trade-off between, you know, the making the system fully bulletproof to covering a percentage of the utility power events. Because maybe if you cover 90–95% of the utility power events for a customer, that's enough to get them past their losses and their downtime that they were looking at. Because that's what you weigh the cost of the ride-through against: customer losses in products, downtime, personnel safety, things like that. Ultracapacitors are maintenance-free, as with electrolytic capacitors. They have a long lifespan. 1,000,000 charges, discharges is the specification we get from the Ultracap companies. Here's some short-term or capacitor solution configurations. Over on the in the bottom diagrams, the left is a 60 horsepower 1 second full AC line loss. This is a wall mount cabinet, and it can have a display, or it doesn't have to have a display. But once again, I recommend that display. So the energy storage can be put inside with the electronics in a lot of cases if you're right around 60 horsepower or below. When you get up into the higher kilowatts, you have to look at two cabinets. One would hold the electronics, which actually includes all the modules except for the capacitors. It's going to include the discharger, charger, voltage regulator, booster, and the Ultracaps will go in the cabinet next to it. We can actually mount the cabinets, the energy storage cabinets on the back side, which is what we did for Samsung. So there's some of these things are, need to be worked out prior to quoting, and that would be one of them. How do they want to configure the cabinet system? They want a double bay, or they want back to back, or how much room do they have to install a full ride-through UPD system? And we can also, if they're going to integrate the modules, we can assist them in any kind of issues they'd have with that also. Make sure they have the proper drawings, documents, and everything else they need to be able to integrate their own system and connect their own energy storage. Here is the short-term outage ride-through block diagram, and we come from the AC line through the disconnect, which once again disconnects the full system, energy storage, everything from the variable frequency drive, which is very important for maintenance and for having to get into the cabinet when you want to lock out, tag out the drive and the ride-through system to be able to work on it. Through the ride-through disconnect, the next thing is the fusing, and then the isolation transformer that's for the charger. The isolation transformer is connected to the front of the charger. The charger is also fused, and the charger is connected directly to the ultracapacitor bank. And then connected to the ultracapacitor bank is the discharger, which is basically a braking transistor and a resistor. The discharger will discharge the caps within seconds, and then it's safe to be able to open the cabinet and get in and look at things and do maintenance or whatever you have to do. Then the voltage regulator is connected to the other side of the ultracapacitors or energy storage. It pulls the energy out of the cap bank, rectifies it, boosts it, and puts it to the DC bus positive and negative connections of the VFD. Once again, you're connecting the VFD right across the DC bus at the bus capacitors. This gives you a little more detail about the layout of a cabinet. This can help if you have your own integration capabilities. Connects to the drive's DC bus terminals, as all the ride-through does. And one UPD can support multiple drives. If you've got multiple drives in one cabinet, you can set a UPD rated for all of the drives, up to 610 amps in a single cabinet, and we can master slate any of the ride-through solutions up to higher kilowatt ratings. Single unit, 250 kilowatts. Once again, if you have any questions or comments, text them to me. I'll try and address them right now. If I can, I'll send you an email later on. Or if you don't want any further information on ride-through and specification, but I think pretty much this covers everything you're going to need for talking to the customer, specifying the ride-throughs. over the past 2 sessions, being able to look at indications and your basic ride-through information up to the point of tearing a unit apart and fixing it component by component. Long-term outage or battery ride-through, greater than 5 seconds now. There's an update to this. And we say 30 minutes plus. Well, that just means we can do any amount of time, but you have to keep in mind that the higher the time, the more the batteries, the more expensive the solution, with energy storage being the most, or at least half of the cost of the total ride-through solution. Another thing to consider, the customer, if they're using battery energy storage, there has to be a battery maintenance and hazmat program involved. And also, if you decide to integrate batteries into your own cabinet, there are special considerations. Batteries vent gases, and the gases have to have a way to get out of the cabinet. So there's a little bit difference in battery cabinets and regular electronic space. So if you're going to do your own energy storage, hopefully you have enough information on how to set up a battery cabinet, but we can also help you with that too. We've done a lot of battery systems over the past few years, especially in the United States. And as I said, in the United States, SAGs are the main spec, but some companies have a global spec, is what I'll call it. Good example is Microsoft. We did a data center for Microsoft, and they have a spec that's standard all over the world. It's something their engineers settled on, and we just make recommendations and then finally give the customer what they want. Sizing battery energy storage. The DC bus of the drive, the battery bank has to maintain a certain voltage to be able to boost into the DC bus of the drive. Remember, it's a 2-to-1 booster, so we don't have to have the full DC bus voltage. A couple examples of line voltages here in correlation to battery banks. 380 volt to 415 volt AC line is going to be 432 volts DC battery bank. Now that translates to basically 36 batteries in a string, 36 12-volt batteries. So usually when we specify batteries, we look at the kilowatts, the time, and what the DC bus battery bank has to maintain to be used with the ride-through booster. 460 volt line would be 480 volts DC battery bank, which is 12 volt DC, 40 batteries in a battery string. Usually when we specify a long-term outage, we're looking at the specification of utility power out or AC line voltage out to gen set up. And that can be anywhere from, depending on the type of generator, from 5 seconds, and I've had specs that were up to 30 seconds because they wanted several restarts capability of the generator. So they want the ride-through to back up that time so there's no bump or there's no drop of the process between utility power out and gen set up. So we run into that spec. It's fairly common. A little quick review about batteries, and then we'll move on to something else here. The only other thing that I haven't pointed out before is battery disposal can also be an issue. Usually you're not worried about that. Between 3 and 5 years, battery string changeouts usually occur depending on the battery manufacturer. They say 5 years. When I talk to the plant people that have batteries they're using for ride-through or for UPSs, they usually end up changing them out around 2 to 3 years, depending on how beat up the system gets or how many times the UPS is activated or the ride-through is activated. some of the things that cause early wear and tear on batteries. And these are actual instances that I've collected from talking to customers that have had have UPSs or have had some sort of dealings with batteries. What happens is batteries a lot of times are forgotten. They're just left there because what happens, you don't use them all the time. And usually long-term outages are not a common occurrence. So you're not going to know the batteries are bad until you have an event and the batteries don't work or the UPS doesn't work. So it's very important that the customer maintains his maintenance, checks his battery levels. You have to change out the full string when you're changing out batteries. They all have to be similar. So another thing, maintenance contracts expire. Somebody doesn't catch that. Maintenance personnel change. You may have a really diligent guy, and then the next guy, lets the batteries go bad. And also, going back to the Bonitron connectivity, series solution batteries will receive more wear and tear than parallel standby systems utilizing battery energy storage. So one thing to consider with a series solution is constantly passing the AC through the batteries, through the UPS to the front end of the drive. Whereas we sit in a static state and we're not activated until there's a ride-through event or threshold. So you're constantly beating up the batteries going through a double conversion UPS. Any kind of deviation in the AC line can cause the batteries to activate. So they can get beat up even though there's not a full need for a full outage ride-through event. And as I said, usually UPSs start at 5 minutes. You may not need 5 minutes. So we can actually size the batteries to the actual time and spec you need. So you're not stuck with overkill or much more than what you actually need. Now, about the DD4 display kits. They come in kits now. We can do a remote display, which can be connected to the front panel of a drive cabinet if you're going to use a single sag ride through. And we'll send the whole kit that has everything you need to be able to connect a remote display. Or they come with the UPD full cabinet system. Some of the parameters you can monitor with the DD4 display: ride-through event statistics, individual ride-through events, or lifetime ride-through events. So you can actually see what your utility power is doing or your internal plant PQ is. So it may help you to be more specific about your requirements for later installations. Or it may cause you to realize that you need to retrofit the sag ride-through with outage ride-through ultracapacitors. Okay, the system will ship with record of a single event, and that's what we use for testing. We test them with that and then ship them with the event logged into the DD4 display. This says 100 most recent fault states. Actually, it's 30. That's a typo. The actions manual, there is a test initiate, and the ride-through test can be done online because what it does is it raises the DC bus above the nominal level during the test. This isn't an actual ride-through event. You're actually raising up the level, and that's telling you if the test is successful that the ride-through is boosting. It will raise up the bus just high enough to test the ride-through, but not high enough to trip the drive on over voltage. There's also a threshold check you can key into the display. All of these functions are outlined in the owner's manual for the DD4 display that's located on the website. And also it will monitor DC bus voltage fault logic. So in other words, it will let you look at the parameters of the AC line, DC bus, all the different parameters around the ride-through. And then there's timer settings also. So you can set the time to be able to know exactly when the ride-through event happened, and status timer also. In the kit, these units the DD4 display can be ordered in a module kit. If you want to provide a remote display that goes out to the front panel, or if you want, or this kit will be included in the UPD system and mounted and already wired. The kit includes a DD4 HIM, an I3 interface module that interfaces with the ride-through system, and current sensors that monitor the lines that connect the DD4 display, which will provide parameters back to the control circuitry and back to the interface module that will tell if there's any kind of issues with the connections between the displays. The current sensors are included. This shows a little bit better drawing where the current sensors go, and used for monitoring the current levels, provide indications of a fault, and as I said, they're configured as per the DD4 manual. We make sure you have the current sensors vary with the different ride-through current ratings. So the current sensors are matched up to the actual ride-through that's been specified. As you can see, the connectivity goes between the DD4 interface module. Current sensors connect to the ride-through bus to be able to monitor the bus DC bus voltages, and it also monitors the charger charge current, and it shows you the pinout for the actual current sensors in the bottom of the page. That's all included in the manual that's indicated by the icon. Now this shows the cabinet system for the batteries. On the left is the energy storage bay. As I said, when you get up around 50 kilowatts, 60 horsepower, we have to start separating the energy storage from the electronics bay, just due to size. So the batteries will go in one cabinet, and the electronics will go in the other cabinet. And this shows you a cutaway view of what's in the cabinets: a voltage regulator and charger, along with the isolation transformer, go in the electronics bay. We can also put control power circuitry in the electronics bay, and we can put common bus ride-through diode modules, which are required when you're tying together multiple drives on a common bus. And for the battery systems, there is no discharger required, of course. And now some installation considerations for ride-through as a standard. All the ride-throughs, this applies to all of the different ride-through types. The size of the ride-through is going to depend on the kilowatt rating required, which comes from your motor specification, what's required from the motor as far as holding it up during a ride-through event, and the energy storage. And we will put any kind of control power option in the same cabinet, AC or DC. Enable circuitry is in there. We can do NEMA 3R, NEMA 4, any kind of NEMA rating. If it even needs to be, NEMA 4 washdown, we can handle that. One consideration is if you're going to mount it in the same VFD cabinet, you want to look at the watt losses between the two. But the ride-through voltage regulator booster and the other ride-through modules, the watt loss is about the same as the VFD, depending on the size of the VFD. So that could double the watt loss, but usually you're not past an allowable level even by using the ride-through. especially if you're using the single unit sag ride-through. When talking about ride-through common bus, the M3460D units are required to tie the inverters together at the DC bus. They're going to be specified for the number of drives or number of drive connections required, determined by the amount of inverters that you're going to be tying together. And you can also use line regen or dynamic braking also. If you're going to use the line regen, you might want to consider using the regen diode modules, the CBMs or common bus modules. But for the most part, if it's just a ride-through common bus, you would use the M3460Ds. And this shows the connectivity. This is a 2-drive common bus. As you can see, positive and negative connections from the VFD to the diode module. And the diodes connect over to the DC plus and negative of the ride-through unit. You size the M3460D to each leg is going to have to handle the current from one drive. We have a full module rating which takes into consideration the amount of drives, the total drives, but the important part is making sure that you size the diode module to handle the maximum current per leg. So we have modules that go up to 6 drive connections, and we can parallel those for greater. I've done up to an 18 servo drive ride-through before. So we paralleled several of the 3460s together. Those can also be mounted in the cabinet system. Now, one thing to be aware of is since I've been here in 2000, I've seen this maybe a couple of times to where we had to use, when we were master slaving ride-through units, we had to use a diode network on the positive and negative bus. That usually depends on what the plant power is doing, or if there's any kind of circulating currents or anything like that. What happens is there's extra voltage on the negative line of the DC bus that we can isolate with diodes. And what we're doing is we're isolating between the inverter and we're isolating between the ride-through, just to kind of stop the possibility of high negative DC bus currents. Now, as I said, I've only seen this a couple times, and it wasn't in the United States. And my hunch was that it was something with the configuration of the drive that they had, or their power lineup. So this is just something to keep in mind if you run into this, but chances are it's not a real concern. And as I said, we've only dealt with it a couple times, and it's only when you master slave M3460R units. If you're using energy storage ride-through, this is not an issue. The short-term or long-term outage, it's not an issue. It's just when you have multiple master-slave sag ride-throughs connected to a drive. Okay, now as we said, critical applications is what we look for. And all of these issues apply that I've talked about so far to all of these applications. And here's some of the applications we've done to give you an idea of what to look for. In general, when we say clean rooms, we're talking about pharmaceuticals, we're talking about semiconductor, anywhere there has to be a pristine, controlled environment. And the reason for the ride-through with some of these environmental systems is you can't have any deviation of the atmosphere, particulates, things like that in the air. And what they look at, say in semiconductor, is they'll look at the cross section of a human hair, and then they'll look at 10% of that size as far as a particulate that's too big in the air that could corrupt the wafer etching process. So, you know, this also goes for chemical processing and things like that, to where there can't be any corruption in the environment to the process. Cooling water systems, the chill water that goes to the machine tools for the wafer etching has to be consistent. There can't be any change in flow to the machine tool, or the machine tool will detect that minute change and shut down. And what happens is when it shuts down in a clean room, all of the products in the clean room have to be disposed of. They're considered scrap products. They don't even worry about testing them, they just pitch them out. So that's why you have quite significant losses in a lot of critical applications. Some of the other critical applications, synthetic fiber spinning, that's where you can lose product or manufacture a grade B product all afternoon if you're not paying attention to the speed and torque of the motor. Semiconductor fabrication we talked about. Turbine lubrication pumps, this is more of an equipment safety issue, which you run into a lot of times. Sometimes you can't have any deviation of the lube oil going to a gas turbine, because the turbine can burn up in a very short time. So you have to keep that constant lube oil flow to the turbine to keep it lubricated so it doesn't overheat. So there's a lot of applications out there like that have to have consistent either lubrication oil or airflow or chill water flow, and they can't have any deviation. And that's the applications you look for when specifying this stuff. And of course, you weigh the cost of the downtime, product damage, to the cost of the ride through. Also, a fairly new one over the past few years, oil field extraction pumps, or PCP pumps. This is also an issue of equipment damage. When you have a long line going down into the ground that's pulling up oil, what happens is when the drive that's doing the pumping shuts off, the line that goes down into the oil reserve there will backspin and create regenerative energy, which will trip the drive on overvoltage, and it can also damage the pumping line. So there's two solutions for this. Either you deal with the regen and restart the drive, which can take up to 8 hours to restart, because you have to let all the oil drain out into the line. You can't start it under full load like that. Or you ride through the event and put a safety brake on it, like a dynamic braking resistor, in case it doesn't ride through the event and it still has to deal with the regen. But the actual best solution for this is to just ride through the event, which usually are anywhere from 1 to 2 seconds. And then you don't have to restart it and you don't lose production. Once again, this shows the layout of a lot of critical environmental systems. This is a data center. You're going to have a UPS backing up the whole thing. Then you're going to have a generator backup and a UPD process level. And the purpose of this is to hold up the HVAC system. And this just shows a clean room. And here is a pretty much standard chill water system. Data centers, anywhere you're gonna find this type of a lineup. And this is a good application for common busing several drives on one UPD. You can cover the air handlers, the chill water, cooling tower, all on the same DC bus. You size the ride through to cover all of them. Maintaining environmental conditions in data centers is the critical issue here. The racks, if they're not being properly cooled by the HVAC system, can get extremely hot and destroy data, and destroy the data racks and the servers. we've talked about semiconductor. The two applications are air handlers and chill water to the machine tools. Specification, usually in semiconductor, but I've been seeing this requested a lot in other critical type applications. Ride-through, in general, is you're always being requested for third-party testing. A lot of times, the customer will want to get a unit, and they're going to want to test it on site, and we will provide a demo or consignment unit to be able to do that. We can also provide tech people or engineers to be able to assist with that. We just got through testing the SAG ride-through with compressors, and it's a special type of a super compressor, so to speak, and we hook up the ride-through to the inverter section of the combination inverter compressor motor. It's one combination unit. We did testing on that, and now it's become a popular solution for critical refrigeration, and where you can't have any change in the compressor speed or the compressor output. So the point to make here is that a lot of times you're going to run into this request from customers that want to check it out first before they use it, and we're okay with that. We've done that many, many times. We're certified by several different third-party organizations, and the ride-through is also UL. And the interesting thing about the UL requirement is we never had a request for it in the United States. The reason we got the UL was because of Taiwan semiconductor requirement. This just shows what third-party testing looks for when they're testing ride-through. They look at sag depth and they look at time. And this shows the SEMI F47 test, and we actually go above and beyond SEMI F47. The requirement is only 200 milliseconds, but Bonitron sag ride-through will cover the red line, which is 50%, for 2 seconds. You look at the red dots, those are the test points that the third-party organization tests for to be able to say you're certified to handle the SEMI F47 spec. And this also shows you the relationship of the actual sag events to outages or longer term. And if you notice, the majority is within the SEMI F47 specification. This data was taken from the Tennessee Valley Authority in the southwest United States. This is the ride-through we did in Austin, Texas for Samsung. As I said, they have the vaccine spec, which is definitely a greater spec than SEMI F47. Energy storage, one cabinet, all the components in the other cabinet. It was for cooling water systems for machine tools, 150 kilowatts for 1 second. Most of the time you're going to run into specifications that just cover SAGs. In this case, both Intel and Freescale required SAG ride-through. We provided a full cabinet system, single unit, backed up the motor, just to maintain constant air and water flows for product quality. This shows you the correlation between regional type specifications, 90-second full outage overseas in the Asia market, to a 2-second 50% sag in Singapore for semiconductor. The interesting thing about this is the same company that we did the sag ride-through in Singapore required full outage in the United States. So specs can vary with companies, but mainly they're geared around the utility power event that's going on in the region, how stiff the grid is. Half a second ultracaps, and If this is the fibers and textiles industry, which is probably the most applications we've done in the United States. Over on the right are all U.S. applications, and this is where the ride-through all began back in the late 70s. We provided the first ride-through for DuPont, which is now fragmented into Kordsa and Dusa and several other companies, and we're still providing ride-through to this day for Chattanooga plant, Kordsa, and several DuPont plants out east. And they always request SAG ride-through because they're only looking at momentary brownouts in their particular region and area, which is pretty common in the United States. Injection pumps, position fiber lines, fabric rollers, and tension systems are the requirements that they put ride-through on. And going back to the application I mentioned earlier, this is the PCP pumps. We're seeing a lot of U.S. companies getting involved in pumping applications globally. I've specified probably 3 or 4 of these, and it's usually right around a half a second, and it's always ultracapacitors. And the return on investment is dependent on the price of oil. And I know it's fairly low, but when it was at $50 a barrel, it was a 2-month return on investment. And everything went in one cabinet. It was a half a second, 60 horsepower application, and that shows you a picture of the actual PCP pump and the coiled pumping line that goes down into the ground. That's the big concern when it trips on undervoltage. Turbine lubrication. These specifications usually are full outages and they're long term. We haven't had a turbine lube system spec that was doable with ultracapacitors yet. The specifications are always long term. This was actually the 4-hour spec that we were requested for. And just a quick review of configuration, and then we're out of here. Determine drive types and ratings, AC line voltage, drive horsepower, kilowatts. We don't care. You can even give us amps, and we can take the parameter and figure out what it is from there. Make and manufacture of the drive, kind of important, but not critical. It's just good to know if there's anything that's going to bump heads with the ride-through. DC bus connections available, that is critical. And control power for the drive. Once again, if you don't back up the control power, backing up the drive does you no good. Weaken common bus drives, and just some of the control power schemes that we deal with. For 115 volts, you might want to add a small UPS or dip-proof inverter. And for 24 volts, we have a full line of either full outage backup or SAG outage backup. And that's dealing with control power in 24 volt or 115, 120 volt. This shows a correspondence between the smaller cabinets, 10 to 50 kilowatts, energy storage, and the electronics can go in one cabinet. And then the 2-second SAG single units that can go in the VFD cabinet. And that shows the one in the middle, 12 kilowatt, which is a battery system. Here we provided the battery modules from us because it was a smaller system. Usually for the big cabinets, we go out to a battery vendor. For the smaller 50 kilowatt and below, we'll provide our own battery modules and source the batteries only. And over on the right is the 1-second full outage 150 kilowatt. And that's pretty much all I have. I see a few questions here, so hang around. I'll answer your questions. If you have anything else and want to get into a little more detail, I'm at tsmith@bonitron.com.